by Al Klase, and the topic is going to be antennas and grounding procedure.
Yes, thank you, Tom. What I didn't tell Tom is that the subject is slightly messed around, but ultimately we'll get to grounding and such like. I collect shortwave receivers, communication receivers, and the like, and do a fair amount of shortwave listening. And over the years, I've developed some thoughts on antennas, and I'd like to give that to you tonight. I've got a limited number of reprints of this thing. You can share them. Tom has an original, and maybe we can get some more made if we need them. Nothing can make a good radio sound bad as quickly as hooking it to a bad antenna. I think you've all experienced that. You take your stock Philharmonic and break 3 feet of wire down the back of the table and turn it on, and well, you secure WLR and maybe the BBC. But when you try to really dig down for a signal, that works well. Throughout the 1930s, there were a lot of radios built that were so-called all-wave radios. Some of them even covered on down into the long-wave band, below the broadcast band, and typically they tuned up to about 18 megacycles, as was said in those days. And the introduction of these receivers caused major companies to develop effective receiving antennas to be used with all-wave sets. These designs have been largely forgotten, but they are documented, and they can still provide really good performance for those of you who want to listen to your radios. And we'll go into these a little bit tonight. We'll start out talking about antenna basics. We'll take a look at some of the real fundamental problems with ordinary antennas. And we'll take a look at some of the classic solutions to those problems in terms of receiving antennas. Most of the conventional wisdom around that you run into these days concerns transmitting antennas used in amateur radio. And the problems they face are different from the receiving antenna problem. And so, like I said, there's been a lot of information that's been sort of lost in the age of television. Some basics. What does an antenna do? And in fact, we need to consider antenna systems. That is the antenna, the feed line bringing the signal into your set, the ground system if there is one, and whatever other components make up the antenna. And the mission of the antenna system is to reach out and capture a good clean signal and deliver it to the set without picking up a lot of noise along the way. We'll take a look at the two classic antennas, the Hertz and the Marconi, and then we'll take a look at some other useful antennas. The Hertz or Hertzian antenna dates back to good old Heinrich Hertz, and he's probably the first guy to build an antenna that had even an inkling of what was going on. His antenna looked something like this. He had a high voltage spark coil here, so his signal generator was right here in the middle. Two essentially symmetrical elements, and the distance from one side to the other of this thing is a half wavelength. Picture over here, a piece of wire between two insulators. These curves here are showing the voltage and current distribution along the wire at resonance, and it's not real important to understand that, except that at the center point, the voltage is at minimum and the current is at maximum. So in other words, it's a low impedance point. This is where you normally feed one of these antennas. And the voltage is maximum at the end. And of course, at the end, there's no place for current to flow, so it's zero. The one thing in this Now, most of these graphics came from 1930s publications, most of them from Girardi's radio servicing book. Important thing about a resonant antenna is the greatest amount of current flows in the antenna when it's resonant. But conversely, current flows in antennas at frequencies other than where it's resonant, and for receiving purposes, enough current flows that you can use an antenna pretty far off resonance and still have it function as a receiving antenna. So, Marconi antenna is half wavelength long, typically fed in the middle, but there are some schemes for feeding them from the end. And it operates, it can operate completely divorced from ground, so that may or may not be an advantage. The other basic form of antenna, developed by Marconi, you take a single conductor, stick it up in the air, and the signal is applied to the bottom of the conductor and to the ground underneath. What happens electrically, if you have a good ground, is that the top half of the antenna is actually reflected in the ground, and so appears to be a Hertzian antenna, in fact, while it is only a quarter wavelength tall. Marconis are typically vertical antennas, or sometimes they are L-shaped antennas, wherein the vertical section radiates and the horizontal section increases the capacity to ground, which causes them to radiate still further. So, Marconis and Hertz antennas are the sort of things that amateur radio people use to transmit at higher frequencies. They'll use a dipole, a Hertz antenna, and at the lower frequencies where that becomes cumbersome, and also where they want vertically polarized signals, they'll use Marconi antennas. Marconi antennas are also used for AM broadcasting in almost all cases. So what's wrong with these antennas for reception in the home environment? Well, here's one of the big problems. Near the top of the broadcast band, half wavelength is 300 feet. Your backyard probably isn't that deep. Even if you go to a Marconi antenna, vertical antenna, quarter wavelength down at the bottom of the broadcast band is 375 foot thereabouts. You're unlikely to erect a tower that large in your backyard. I'm sure the zoning people would have a field day with that. So it would appear you're in trouble. However, a couple of saving graces. In the broadcast band, especially in the broadcast band, and on up through the shortwave frequencies that are used for international broadcasting, the background noise level is quite high. And what that means is that the signal-to-noise ratio of the incoming signal, no matter how good your antenna is limited by the background noise. And also, most vacuum tube receivers are really quite sensitive. They're far more sensitive than they need to be, considering the amount of background noise. So for that reason, you can get away with a receiving antenna that is much smaller than the resonant antenna designs we've looked at, like the Marconi and Hertz. Also, because of the amount of gain you have in the receiver, signal-to-noise ratio is much, much more important than the actual strength of the signal coming off the antenna. So what you need is an antenna that will deliver a good quiet signal to your radio. So a modest-sized antenna can give good results. Okay, let's take a look at the old standby. The antenna that everybody knows about. The antenna that was erected in the 20s and 30s for most of the broadcast receivers. Notice the inverted L. Piece of wire comes out either under your window or maybe through a a ceramic tube with hole drilled in the window frame, leading wire up to an insulator, other wire and an insulator out to the highest thing you had, the tree, the garage, maybe the electric pole. Antennas of this sort work reasonably well for broadcast band. They work reasonably well for shortwave. A lot of people call these antennas long wires. That's really a misnomer. A long wire antenna is defined as being multiple wavelengths in length. What I prefer to call these is random wire antennas. You put them up, the length is how much space you have, and they can work pretty good. Other point here is you have ground wire. This is in fact a Marconi antenna. It's worked against the ground. Two wires run to your radio, one from the antenna, one from the ground. Also, some sort of lightning protection is indicated here. Maybe at some later time we can go deep into lightning protection. For most installations like this one, the house, the trees, the electric lines are all a lot higher than the antenna. The likelihood of taking a really major strike to that antenna is very slim. However, it's a good idea to have some sort of protection to take care of a secondary strike from the tree to get over. If the antenna were up and in the clear on top of the mountain, Katie barred the door because nothing's going to save you when you get hit. So what's the problem with the inverted L? What's the problem with most of the antennas you might try to work on? Girardi called this the interference zone. Turns out that your house is full of electrical wires, and some of those electrical wires are connected to noise sources. In the old days, it was things like the universal wound motors in fans that had sparking brushes. These days, it's computers and all the other various electronic things you have in your house. Solid state fluorescent lamp ballasts, light dimmers, all that sort of stuff. And they all result in RF energy, which is conducted. This IC is current of conductive interference along the wires within the house. And then each one of those wires passively couples or radiates signal to the outside world. And so what happens is your cozy little house has this nasty little cocoon of noise around it. You don't believe this? Take a pocket radio, walk up to a light switch. Okay. If you try to get away with a simple antenna, well, let's get more sophisticated than the 3 feet of wire hanging down the back of the set. Let's ground the set. Let's run some wire up into the attic. All of that stuff is within the interference field. The antenna will work better than the 3 feet of wire, but it's still going to be noisy, and it still isn't the best thing you can do. Also pay attention to the fact that the ground lead is half of the antenna system, and if it is in the interference zone, it's going to pick up noise as well. So that's another consideration. Okay, how can we beat the rap? Put up an inverted L and run it out away from the house into a more interference-free environment. Better yet, make the antenna longer. You've increased the ratio of antenna in the clear to antenna in the noise, and the signal-to-noise ratio gets better. So, from a simple standpoint, put up an inverted L, get it as high and as clear as you can. Makes a pretty good antenna. But you always have a problem of this lead-in coming in through the noise zone, and you end up picking up extra noise here. I've been struggling with this problem. I like to listen to WNYC 820 on Saturday afternoons. There's this old guy named Danny Stiles that they drag out of a formaldehyde tank. He plays really nice old records from 2 to 5 o'clock. But I got a lot of noise, and I'm just now coming to where I'm beating the noise.
Why don't we just put a shed out in the backyard, put it under the shed?
That's it, just go out into the shed. Okay, how can we beat the wrath? Here's an idea. Let's shield the lead-in wire. Let's use a piece of coax or put a piece of pipe around it or something, and we'll ground that shield. It's interesting, in the old days, they grounded that shield through a resistor in this particular application, and I'm still not clear on exactly what that buys you. But now, the signal comes down through the shielded area and cannot pick up noise as it passes through the interference zone coming to the receiver. There is a problem, however. Your aerial, your antenna, especially a short random wire, one that's less than half a wavelength, looks capacitive. That is, it's as if there's a signal generator out here feeding in this way through a capacitor. Also, the conductor of your shielded cable and the shield form another capacitor, and what happens is this clean signal that comes in here, a lot of it gets grounded and goes away. You in effect have a voltage divider of the antenna capacitance and the cable capacitance, which attenuates the incoming signal. So this antenna, which is fairly short for the wavelength, is a really high impedance source, and a lot of the signal is lost in the incoming lead-in. It may still be a better deal than your standard inverted L. Give it a try, run a piece of coax out to the antenna. Just a little aside here, the way to get antennas working good is to experiment with them. And the primary way to do that is build yourself a little switch box and hook one terminal of the switch to the antenna you're using now, hook the other terminal of the switch to the antenna you're working on, and pick a couple of stations you want to listen to, and just listen to whether you're making headway. Listen to whether the antenna is better than the old one or not. It's the way to do it. Okay. How can we solve this problem? And this is another problem that was solved in the 1930s. Let's put a transformer up at the end of the cable. Auto transformer, it's a step-down transformer. You have a lot of turns up here and a couple of turns down here. So now the high impedance aerial feeds the transformer. Low impedance tap off the transformer feeds the cable. And in fact, then they have another transformer down at the radio receiver to step the impedance back up. Steps the voltage back up to feed to the radio. Because most of the radios were designed to work directly connected to the high impedance antenna. So transformer at both ends, clean signal comes in here and then it's protected by the cable, delivers a clean signal to the radio.
What were they buying? What were they effectively transform up and down?
Okay. The cable, are you familiar with the term impedance?
Yes.
Okay. The cable has an impedance of maybe 50 ohms, 75 ohms. The antenna has an impedance of hundreds of ohms. 300, 400, something like that. And so when you connect a 400 ohm source to a 50 ohm load, you don't get maximum energy transfer. You lose a lot of your signal. So by using the transformer, you can improve the situation considerably. At the bottom, the radios, the input of the radios is about 400 ohms.
Oh.
So if you're really going for signal strength, you can step it back up at the bottom. Might not be, probably not really necessary. The radio will be pretty happy just looking at the clean signal out of the 50 ohm cable.
Wouldn't that create so much of an input that you're going to wind up overloading the front end of your set though?
Probably not. Most vacuum tube radios are pretty tolerant of input overload, and almost all of the more modern radios have automatic volume control, which pretty much takes care of it.
I've seen cases, I've personally experienced cases where vacuum tube sets, especially if you're using like a 58 tube for an RF amp, to wind up overloading that tube. I've seen it happen, that's why I was wondering at what point do you...
Yeah, if you have that kind of situation, what you do is you add some resistance down here, cut your clean signal down and still keep it clean. Okay, so that's some ways to fix up the random wire antenna so it works better. As I alluded to earlier, in this time period, there was a lot going on in the area of shortwave listening and shortwave radios. And the international broadcast stations in those days were not as powerful as they are now. I mean, if any of you guys who have played with crystal sets recently know that you can hear the BBC on a crystal set, okay, or Deutsche Welle all the way from Germany, and the only power you have is what comes down the antenna. The broadcast stations in the old days were not that powerful, and so you had a tougher job for the receiver and the antenna system to get you reasonable performance. And one of the things they used was the so-called doublet antenna. Doublet is same as a dipole. I think maybe if you were really picking nits, a doublet is not necessarily resonant, while a dipole usually implies that it is. It's the same piece of wire and it's the same antenna. And typically they feed them with a balanced feed line. That is, two wires. Usually it was twisted pair. In this illustration, it's not drawn to scale. The distance between these two wires is really quite small. You'll also notice that there is a transformer at the bottom of that line so that neither side of the antenna is connected to ground. And the advantage of this scheme is the following. The incoming radio signals that hit the antenna cause a current to flow. And if you look at it at any particular instant, that current is flowing in this direction, in this element of the antenna, in this direction, in this element. You'll notice the current flows in opposite directions on the feed line. And down here, it flows through the transformer primary. The noise signals, however, that are hitting the feed line, because they are very close together, the same signal hits each of the wires of the feed line, and the noise currents are traveling in the same direction on the feed line. Thus, they are balanced out, and they cannot generate a signal in the primary transformer. So, you have your doublet aerial up in the air, collecting clean signals, and the balanced feed line bringing signals down to the radio.
Two questions.
You eliminated the noise. It's a noise canceling situation.
Two questions. One question about that. In the aerial portion,
Yeah.
in the center between the two leading wires, is that a piece of insulator, so you have one aerial going out and another aerial, or this?
Right, and an insulator in the middle.
And an insulator in the middle. And the actual distance, or the actual gap of the two leading wires, it would be maybe a very, very tiny distance?
Very, very small. I mean, most of the 1930s doublets were fed with twisted pair wire,
So you can actually take two and twist them
wrapped together. Or one of the things you can do is you can use 300 ohm TV lead-in. Very, very successfully. Okay. Now, what's wrong with the doublet? A couple of things. Let's look at this middle curve here, the two-hump camel. The doublet will give you real good reception at the frequency at which this distance is a half wavelength. Okay, in this particular situation, it's resonant around 8 megahertz, and that gets you good reception down around 6 megahertz, which is the 49 meter broadcast band, and also up at 10 megahertz, which is the 31 meter band. However, a doublet antenna, when it's a wavelength long, is a very high impedance at the middle here, because it's two half wavelengths. Now you've got a high impedance point here and here. It does not deliver a lot of signal. And that's what this trough is showing you in here. However, at 3 times the resonant frequency, it works well again. And in fact, if you took this up in frequency, it keeps waving on out. But for shortwave broadcast reception, that's about as far as you care to go. So you have this problem here around 19 meters, which is a 15 megahertz, which is a very popular broadcast band, but that antenna isn't going to work so well. You also have another problem. If you want to use this on your broadcast band radio, all doublets become really bad below their fundamental frequency. They roll right off, and by the time this guy gets down to the broadcast band, it's a non-antenna. Doesn't work well at all because the wavelength of the broadcast signals is really long, and the 2 halves of the antenna essentially see the same signal, so nothing comes out of it. So there's a problem there. The solution to the first problem is to build, in addition to this 2-hump camel, you build yourself a dromedary in here, and you hook them together, and now the overall response looks like that. It's fairly flat throughout the frequencies you're working on. And this design showed up in about 1935 from RCA in an antenna they called the double doublet. And so what they had here was 2 29-foot sections of wire up at the top, which gave you the 2 humps, shown in the other drawing, plus a couple of 16.5-foot sections down here. Interestingly to note, these are cross-coupled. This element is coupled to this one, and this one to this one. Fed with twisted pair transmission line gives you good shortwave reception. But what about the broadcast band? You know, the radio is going to have to work in the broadcast band, or they're not going to, or for sure your wife's not going to be happy with it. And they took care of this in a very clever way. And it's the same thing that radio amateurs do when they want to use their 4 megahertz, their 80 meter antenna on 160 meter band. Does anybody know that trick?
Yeah.
What do you do?
Twist the lead together and use it as a vertical.
Right, exactly. Except we don't want to twist it on, twist the leads. We want this to happen automatically. And so what they did was they constructed themselves a very clever matching transformer here. We'll take a closer look at it on the next slide. But what this thing does is that for the shortwave bands, we have a differential, what's called a differential mode signal coming down the twisted pair. That is, the current's coming this way and this way, makes this transformer operate here into this secondary, which ends up going to the set. They have another coupling transformer over here, but this one isn't too important. We'll talk about that in a second, but it's not so tricky. But they have a center tap on this primary. Now remember, I was telling you how the noise signals and also the longer wave signals come down the speed line in the so-called common mode. That is, the same signals on both of them, so the current's going the same direction. You pick up that signal on the center tap and run it into the primary of another transformer, which then gets connected to your feed line and goes to the radio. So, what happens here, electrically speaking, is that for shortwave reception, we have this situation. Signal is fed down here. Primary of this broadcast band transformer is real high impedance. It just about doesn't exist. And the signals come down the radio receiver. Meanwhile, down in the broadcast band, the twisted pair wire looks like a single conductor. Like our gentleman was saying over here, you've shorted your coax together at the bottom, and you're going to feed it as a single conductor. And that runs off that center tap down to the primary of the broadcast band transformer and off to your set. Just back up here a little bit. This transformer in the set is interesting in that it's actually two transformers in tandem, one transformer for shortwave and one for broadcast band. And that is in there only because in those days you could not build a broadband transformer that would work across the entire frequency range that you wanted to work with. So they had a shortwave transformer and a broadcast transformer. I'll talk about it a little bit later on. Nowadays, with ferrite, these were all air core transformers. Nowadays, with ferrite cores, that is ceramic, iron-based materials in the cores of the transformers, you can easily build a very broadband transformer. So we can go back and re-engineer some of these old designs. That's that guy and that guy and that guy. Okay, a couple more renditions of the same theme during the 30s. General Electric built some pretty nifty all-wave receivers. I had one of them down here a couple months ago, one that I really liked. They built an antenna to go with it called the D-doublet. One of the problems with that double-doublet antenna was that in addition to the two endpoints up here, you had to bring two more wires down this way. It's kind of messy. It's a lot of wire, all that kind of stuff. General Electric's solution was to use two 20-foot sections of wire which were separated by insulators and a piece of rope in here about 10 feet long. And then their balanced transmission line came up like so and split out in a Y shape, V shape, to the antenna elements. Now, if you think about this, here's what happens. The impedance of that transmission line is established by the distance between the conductors. The twisted pair is 75 ohms or so. When you start splitting it apart, the impedance of the line becomes higher. And so, but as you start splitting it apart, the wires also start looking like the elements of an antenna. I think in the theoretical case, this thing would be a nice exponential curve right here, like the curve on a horn speaker. Anyway, what this antenna ends up doing is that it does not have the deep null that a doublet does. It has only a slight drop off. In modern antenna terminology, it's a quasi-aperiodic radiator. That is to say, it's deliberately detuned by this matching section. Gives nice flat performance through the short wave bands, and then they did a similar trick down at the bottom of the transformer to feed it as a T antenna at the broadcast frequencies. Really clever antenna. I like it. In fact, I was manufacturing these a few years ago. There's about 40 or 50 of them out in the world, made out of 300 ohm twin lead and Radio Shack wire at the top. A little later on, just before World War II, another one of my favorites. I got to build one of these someday because they're so bizarre. The RCA spider web antenna, and they have a multiplicity of doublet elements here to make the thing work across the frequency band. In fact, this thing's only 37 feet across here. This bottom doublet has loading coils built into this transformer, which makes this look like an electrically longer antenna. And then they have a middle-sized piece here and another fairly long piece up here. And in fact, this was just at the birth of FM broadcasting. If you wanted this thing to work at what they call ultra-short waves, like 40 megahertz, there was a kit that would add two more short doublet elements in here to make it cover the FM band. And again, there was another rendition of the center tap transformer transformer down at the set, the receiver transformer. You can trace through that, you'll find out that one of those is center tapped and the other one isn't. Okay. So what happens in the late 20th century here? I mentioned ferrite transformers. Later on, take a look at this. Here's a typical ferrite core. Now, a lot of ferrite transformers are wound on toroids, the donut-shaped cores. To get even better performance as a wideband transformer, use these binocular coil cores, which are like so, with holes in the long dimension of them. You get a really tightly coupled transformer structure in there. So those tricky transformers that were air wound with hundreds of turns of wire can be reproduced using ferrite cores and maybe 5 turns of wire. It's really pretty easy to do. And you can build a transformer that's reasonably flat over 100 to 1 frequency range, like say from 300 kilohertz to 30 megahertz. And there's different sorts of transformer designs doing things like impedance matching. There's a transformer called a balun, which connects a balanced line to an unbalanced line. That can be real handy for separating the shield on a shielded lead-in from the antenna ground system, and thus keeping the noise that the shield's picking up out of your radio. Also, some of the modern things you can use, I like to use 75 ohm TV cable for my lead-ins. It's cheap, it has inexpensive connectors that go on real easy, and there's some nice accessories around, like grounding blocks, AB switches, things of that sort. The accessories that don't work are the splitters and other frequency sensitive things, but using broadband transformers, you can build your own. In fact, I'll leave this up here to take a look at. This is a TV splitter that has a fatter core installed in it, so it now works in the broadcast band. And what the splitter lets you do is bring this nice clean signal that's come down from your antenna on your 75 ohm coax into here and split the power off to 2 receivers. And it has the further advantage that any noise or local oscillator signals in receiver A don't get into receiver B. They cancel themselves out in the transformer. So-called hybrid splitter. And it's a real nice way, you can build them 2-way, 4-way splitters. It's a real nice way to connect several radios to one good antenna and play whichever one of them you want, or play them all at once. Also, 300 ohm TV twin lead can be useful where you need balanced lines. There's also some wide 450 ohm twin lead ham radio guys use. Sort of got ahead of myself there on signal distribution. Like I say, this is a very common concept in TV antennas where you split the signals off to various receivers in various locations. But the TV components only operate down to about 10 megahertz, and what we need to do is build some medium frequency, high frequency splitters and combiners. That can be done pretty easily. Another TV cable concept that's going to be real handy is a distribution amplifier. You have the signal and you want to split it up 6, 7, 8 radios, maybe run other lines down to the other end of your house. The signal's not all that strong in the first place. You build an amplifier to boost the signal before you split it. And again, the broadband transformers are the key. You can build real nice amplifiers without a lot of heartache using broadband transformers. In our next installment, if there's interest in this subject, I'll prepare some stuff and we can delve into a couple of simple designs, maybe some stuff you can go home and do yourself. Maybe we'll get the capacitor guys to order up some ferrite cores if we need to make some transformers. You can give me some feedback after the meeting. We'll think about whether we want to do that or not. Any questions at this point? Yes?
Sometimes with random wire antenna, I find the radio works better with the ground. Sometimes I find it works better without it. Questions?
It's hard to say, and that's part of the problem with sort of uncontrolled antenna designs is that their performance is not real predictable.
Just a random swing.
Yeah, and sometimes you're going to be bringing extra noise in on your ground that may be, degrading the situation. What you want to do is pay attention to signal to noise ratio. Yes, you can hear WOR, but dig down in and listen to WNYC and see if you can beat the noise back on a weak signal. Anything else? Okay, thank you. Sorry for